Alright, we're doing a video for AP Physics 2, and this might be a quick one, this might not, I'm not sure. We're going to talk about Carnot efficiency. I think it's Carnot instead of Carnot. I think it's more French. But we'll talk about the efficiency of a heat cycle. And so let's say you have a car. Alright, so how does a car work? Well, first you need to fuel it, right? And so you have the fuel. The fuel is going to explode in the engine. You missed it, you atomize it, and then this thing explodes, right? So when this thing explodes, the chemical energy is turned into heat energy, and that heat energy is utilized in your car, and so your engine gets hot. It pushes the pistons. The pistons move around an axle, and they hopefully make your car go. And some of that's utilized for like the AC unit it's in the car. Some of it's utilized for the electrical systems, but a lot of it's you're trying to use it to just push the car forward. You know, it's a big car, so this fuel has energy in it. It explodes. It's hot, and then you know what happens with the car? You also have an exhaust. So this heat that's created here, some of it is turned into work. And whatever's not turned into work needs to be expelled, and so we need to throw some heat out, and whatever's left over, what didn't get turned into work, right? So that's pretty much every single thermodynamic system. It's either you're going to utilize heat to create work, and you're going to have to expel heat, or you're going to have to utilize work to move heat around and maybe take heat out. And that would be like a refrigerator where you utilize work to take the heat out of the system, and a heat engine or a heater would utilize heat to add work or do work for you. So this thing called Carnot efficiency is the amount of work that you would get out at maximum from a system. And so it turns out that this efficiency value is based upon the temperature of the hot place where you're getting all your energy from, minus the temperature of the cold place, which is where you're expelling the energy to. You have to have a cold place, because if your car didn't have an exhaust, it would go and, like 1 or 2 times, and that's it. All the hot gas would just be stuck in there, and the cycle couldn't repeat. So the difference in temperature of the hot place and cold place divided by the temperature of that hot place. All right, so this should give you some amount of efficiency value. You might have to multiply it by 100, but it'll give you an efficiency value. So let's say that you have a hot place that is 100 degrees Celsius. So it's boiling water, and you have more boiling water. So that's the cold place, and that difference is 0, which means your efficiency value is 0%, 0% efficient for boiling water and boiling water. You know, you must have a place for this heat to flow to, and the only way the heat's going to flow is if you have a cold place. So let's say that you had a cold place, and it wasn't the 100 degrees Celsius, it was actually a freezing point. So you have like boiling water, and you have a frozen block, and you're going to send energy from the hot place to the cold place, and then you're going to divide it by the temperature of the hot place. All right, so our difference on top is 100 degrees, and the bottom is going to be 100, and so your efficiency is 100%, and that's totally not right because we're in the wrong units. We need to change it to Kelvin. So to change it to Kelvin, we're going to take Celsius. We're going to add 273 to it. So this is going to be 373 Kelvin. This is going to be 273 Kelvin. And we're going to divide by 373 Kelvin. So that one, we still have a difference of 100 on top, but that 100 is now being divided by 373. And so what this tells me is my efficiency, if I have a boiling hot water place and a 0 degrees Celsius place, is that it's going to be a 26.81% efficient system. What this means is if we were to take some of this hot water, and let's say we had 1,000 joules. 1,000 joules. So this is going to be our energy that we dump in. All right. 26.8% of that is going to be, we can turn 26.8% of that into work. So work is going to come out of the system. It's going to be positive work for us, and that's times 1,000, right? So if we have 1,000 times 0.2681, I'm just going to move the decimal over. I don't even know why I'm doing this, but it's 268.1 joules of work that's potentially being able to be done by the system. And the leftover is going to be expelled from the system, so we're going to call it Q out, and that's going to be 713 or 731.9 joules of energy is going to be expelled out of the system. So what this says is you have, again, this efficiency value. The work that you can possibly get out of the system is divided by the energy that you have dumped into the system, right? And this should be, again, the efficiency value multiplied by 100, all right? The work out of the system is just the difference between the energy in and the energy out. And so this turns into very much the same equation, right, of temperature hot, temperature cold, divided by temperature hot. And this is, again, equal to the efficiency of a system. This is a Carnot efficiency. This is the maximum efficiency based on your differences in temperature. So if we wanted to try to get a really, really good efficient system, what this tells us is that we need a really, really big difference in temperature. So let's say we had we had like some kind of reactor where it's like, I'm just going to exaggerate. I'm just making the numbers. We have like let's say we have the sun, like around 3,000 Kelvin. Is that the sun? I have no idea. Let's say we have 3,000 Kelvin, and we are going to have a cold place of like, I don't know, somewhere around 50 Kelvin. Okay? We divide this by 3,000 Kelvin. Right? So 3,000 Kelvin, we're going to subtract 50 out of it, and we're going to divide by 3,000 Kelvin again. This is going to be 98.3% efficient. Still not 100% efficient. So how would you get to 100% efficiency? Well, yeah, you already know. This would have to be 0. But what's the problem of having a 0 Kelvin place? That's called absolute zero, and you can't have it. So basic engineering would say, there's a thermodynamics course, you run the Carnot efficiency, you know your hot place, you know your cold place, this percentage value that you would get is the maximum percentage or efficiency that you could do, you can have in this problem. You can't have any more than that. So in order to make a more efficient machine, you need to have a bigger difference in temperature between the hot place and the cold place, which is why an exhaust is so important. So stop that there. Just Carnot efficiency. Might be interesting, might not. That'll be it.